Kejriwal. He's a gravitational physicist and he has just completed his PhD at National University of Singapore. So, welcome, Shubham.
Thanks, Ayush. Thanks for inviting me.
So, few days ago you posted a plot from your PhD defense of your heart rate.
Yes.
Average was like 93 and the max was 151. You walked almost 2 kilometers doing it. The presentation was fine, but the second half, when the Q&A starts, the line just goes vertical and
Yes.
it keeps spiking on every question. Can you walk me through what was actually happening in your body and in your mind at those points?
So the first half, I can explain why the first half was really not that problematic, first of all, because I had prepared quite a bit for it. So it was like I knew exactly what I had to say. I was well prepared for my slides. So there were no surprises in that first half, which is why my heart rate was quite low. But of course, when you reach a point when, after you're done with your presentation, then you're like anticipating what kind of questions people can ask. That's exactly the point where the heart rate jumps, right? Because now you don't know the next 30 minutes what's going to happen or next 1 hour what's going to happen. Um, I cannot exactly recall what exactly was the first question, which is when the heart rate jumped. But it wasn't as much about the question itself because, as far as I can recall, of the all of the questions that were asked during my PhD defense, I was well prepared for them. But it was just about you know a realization that I am done with the part that I had prepared for, and now whatever happens in the next 1 hour is going to decide the fate of my PhD. Even if the questions weren't as difficult, even if this was stuff that I had prepared for, that sort of like realization what's at stake is probably why I can guess the heart rate jumped so much.
When you are an undergrad, physics looks clean and you solve any questions. There is a right answer at the back of the book. But what was the exact moments during your PhD where the image completely broke and you realized that this is what the modern research actually look like?
I mean, for me, actually, to be fair, that happened before my PhD. So I was an undergrad in Shiv Nadi University near Delhi NCR, and it was a 4 year program. And in the third year, I think they had this thing called undergraduate opportunities for undergraduate research, if I remember correctly. So as part of it, you get to work with like a faculty member in the physics department to, just I don't know, just review like a existing paper or do some hands-on research of your own. And I would say that was already the point where I knew that, we're taught this textbook physics, which is very polished and, everything works. But in real life, it's not that simple because the project I started working on was the cosmic microwave background. So trying to infer, for example, the cosmological parameters of the standard model using CMB observations. And there's this very famous problem in that context of the Hubble tension. So that was my first introduction of, you think your theory is perfect, you're so close to the right answer, but then, a three sigma tension with respect to some other independent observation hits you in the face. Uh, Thereon after, I don't think I've had a single project where I can call it like a perfect one. I have always run into issues here and there, things that tell me that physics is not perfect, and just have to sometimes like do things in a ad hoc way so that things still are sort of on the right track. Yeah, that is my takeaway.
Yeah, because Hubble tension is one of the topic which not everyone know in current scenario. Like there are lots of models, and from every model there is another answer. So when that image breaks, most PhD student panics and try to read 50 most papers. But you reacted by writing custom open source code, code bases. Did you view software development as a tedious prerequisite to get into physics, or do you realize that building the computational tools as a contribution?
Yeah, I mean, I've always been interested in like developing codes and stuff. So I think if I weren't a physicist, I would probably be like a software engineer or something. I mean, I'm not like as polished as a computer science major would be, like in writing codes and stuff. But especially in like a language like Python, when coding is relatively simple, I really enjoy the process. I really enjoy like writing code packages, etc. Um, so yeah, again, I would say like some of this goes back into my undergrad. I picked up Python during my undergrad as well, and the StableEMRIFisher project was, I think, one of my first PhD level code writing project. And I mean, the need for it came about because, well, there were no. So this is like a Fisher information matrix code. We're trying to like calculate Fisher information matrices. I can talk about that more in detail in a second. But basically, the point is it's difficult to calculate them stably. So, in a way that there are no numerical instabilities in their calculation. So we try to write a code to try and streamline the process, take away the human from the process as much as possible, let the algorithm make decisions whenever possible, so as to get like a stable um, output. So yeah, that was the main project. Funny enough, I still haven't written a paper about stable and Fisher. It's been in work for like years now, but yeah, I mean, I always enjoyed coding, and this was just the right project at the right time so that I could do it in the course of my PhD.
And yeah, this is all related to gravitational waves. And
Yes,
yes,
yes.
if we are talking about gravitational wave, we need to talk about LIGO. So for the audience who know LIGO exists, but don't know much about beyond that. So what is the simplest and honest way to explain what GW actually is?
So there are two aspects of GW. There's the detection part, and there's the emission part. So what LIGO does is the detection part, of course. But I guess to understand that at some level, you also have to understand the emission. Um, and you can think of it as a very simple concept. It's just ripples in the fabric of space-time. That's what pop culture throws at you, but I think that's a good enough explanation at a basic level. So these are like waves traveling within space-time at the speed of light. And as they travel through it, they stretch and squeeze space-time in the direction which is perpendicular to the direction of their propagation. Um, so yeah, in principle, it's as simple as that. Of course, because space-time itself is really stiff, general relativity tells us that. This is why this stretching and squeezing is very minuscule, even if these gravitational waves are being emitted from really catastrophic astrophysical sources, like mergers of two black holes, for example. Um, and then what LIGO does is to detect them, it basically um, tries to measure these stretches and squeezes in spacetime. And it does that in the form of a Michelson interferometer. So these are like systems where you have two arms perpendicular to each other, and there's a laser beam traveling through each arm. Um, Generally, the laser source is the same in both arms, so that you can get rid of like laser noise, dephasing noise. And then once the laser beams reflect off of the end of both of these arms and comes back and interferes with each other, um, usually you get a destructive interference. So if you have a sensor, you won't see anything. But then when a gravitational wave is passing through, because it stretches and squeezes space time, this wavelength, the interaction changes, which means that instead of being a completely destructive interference, it's somewhat constructive or something in the middle of a constructive and a destructive interference. And this little, interference pattern is what you really observe in your sensor. And by observing exactly what is the pattern followed by this sensor, you can tell what kind of gravitational wave is passing through, and you can use that to, understand or infer the properties of the black hole, which might have, given rise to such an event. So,
And
of
your
course,
work is to analyze those, which is LIGO detecting.
yes, I come at pretty much the end of this whole, pipeline. So initially, there are people who develop models to understand how exactly gravitational waves are emitted. There are people working in the instrumentation to see how they make it so much sensitive as to be able to detect them. And then at the end of it, once you have detected the signal, are people like me who develop like the data analysis tools to extract information about the true source from the data that you observe. So I work in the data analysis inference pipeline, not specifically for LIGO. The instrument I will particularly focus on is the LISA mission. Um, and basically, we are developing data analysis pipeline tools in order to detect something in the future with the LISA detector.
Yeah. So your work involves, analyzing those data which is coming from LIGO. So what is the process? Like you get the data and then what?
Right. So actually, I am not working particularly on Tango, although I think the pipeline is pretty much the same. I am working on a new instrument which belongs to a Canon 2030. It's called LISA, laser interferometer space-based antenna. The the point is the pipeline remains the same. A little bit about how exactly you do data analysis changes a little bit. But in the crux of it, exactly what I do is you collect the data, and then there are particular stages you have to go through in order to actually detect the signal or draw any sort of information from the signal. So first thing you need to do is actually detect it. So you have to make with some certain confidence the statement that you have actually seen a gravitational wave signal within your data. So, for example, in the case of LIGO, you said something called the false alarm rates or false alarm probabilities. So, for example, you will set it to be something like 0.99 or 0.99. So, what you're saying is I'm 99.9% confident that this is not a false alarm and I'm actually looking at a gravitational wave signal. Once you have done this sort of detection statistic to try and assess whether or not a signal is actually present, then maybe you go ahead and do full inference in it. And there are also multiple ways of doing inference depending on the basically the computational expense that you are okay bearing. One of the simplest ways you can do inference is just Bayesian MCMC. There are these stochastic methods in which you can, sample from the posterior space across a whole range of parameters. And of course, wherever your signal best matches your template, you create a template band. It's called match filtering. Again, some more detail which can go to go more into detail later. But the point is, you try and match a template against the true signal, and wherever in the parameter space your template matches best your signal, that's the point where you call the best fit estimate. And those are the parameters that you say are the most likely to be coming from the source that you have observed, the signal you have observed. Um,
There are lots of templates. Like there is not one
that,
single template. There are lots of templates of
yeah,
GR, right?
yeah, exactly. So I think the most, again, in the context of LIGO, the most accurate way of doing things is numerical relativity. So you
Yeah.
start a few cycles within the inspiral phase before merger, and you evolve through the merger and into the ring down phase. Uh, but numerical relativity is expensive. So you can only have a few points across the entire parameter space from numerical relativity simulations. And then what you try to do is you create some phenomenological templates and you try to tune them to your numerical relativity estimates. So you would say that, okay, at these two template points, which I have calculated using numerical relativity, my phenomenological model should exactly match these. But anywhere in the middle, it should be like a small evolution between the two. So it's sort of an interpolation between the 2 points you've already observed. And that's what, for example, some of the Taylor F2 models, etc., you might have heard of. There is also effective one body models which try to do it at a more fundamental level, try to calibrate themselves to numerical relativity so that they can extend the range of parameters where you have these models available. But yeah, I think in the context of LIGO, they do these sort of like consistency checks where they compare, so they calculate their posteriors using multiple different templates or models, and they try to see whether or not they're roughly consistent with each other.
Numerical relativity is coming from general theory of relativity, which was given by Einstein. Why that is very expensive to solve?
I mean, the idea is very simple, right? You're trying to solve a non-linear. Okay, at the fundamental level, you basically have a set of ODEs that you're trying to solve that are really non-linear, right? So the Einstein equation, um, it is expressed in terms of the Riemann tensor, which is itself expressed in terms of some function of the metric itself, right? And you have to evolve it, you have to evaluate it throughout the evolution of these sources. And then you have to think about like instabilities, what exactly happens at the point of these black holes, right? So you have a closed system. You're not just evaluating how the gravitational waves are emitting, you're essentially like evolving these two black holes. How do you even numerically code up a black hole? Right? So you model it as something called a function, which I am no expert in, but basically the point is to somehow find a way to model them, but then you have to think about the resolution of your simulation as well, because these are just infinitesimal point particles, but of course you cannot have an infinitesimal resolution to your evolution. So you have to basically balance between the resolution as well as the computational expense, etc., etc. It also depends on the duration of the signal that you're trying to numerically evolve over. And all of that, basically, my understanding makes numerical relativity very expensive. It's not just about solving a bunch of equations. Of course, those equations are really non-linear, which makes it hard to evaluate, even for a computer. But at the same time, it also has a lot of different knobs that you have to play with in order to really make it work, essentially. I think that's what makes it really expensive.
Yeah, so let's get back to your work. Like your research is focused on EMRIs, right?
Yes.
Which are extreme mass ratio inspirals. So, before we get into technical details, I want to understand why physicists find these objects genuinely very exciting. Not exciting in grant application way, but exciting in a way where you stay late because you cannot thinking about these objects.
Yeah, I think it's a good question. And I think these courses are very interesting in a few ways. So, first of all, LISA itself, the mission that will launch, that will hopefully see a bunch of extreme mass ratio spirals. The mission itself does not lay out countries as a primary target. The primary targets are MDHPs, massive black hole binaries, as well as galactic binaries from our galaxy as well as from other galaxies. And then I think the third scientific objective, I don't know if that's supposed to be a list of priority or not, then comes extreme mass ratio spirals. Um, so these are sources essentially which are important, but also not of the most important for a mission like LISA. So is the general understanding, at least within the community. That being said, these are still very exciting and interesting sources. I think extreme mass ratio inspired one of the okay. Why are they different in a sense? So at PHBs, you will see a few cycles, few orbits before they eventually merge, and these sources will merge within the LISA band. So you will observe them for maybe like days, 2 weeks, 2 months. But for extreme mass ratio spirals, you will be able to potentially see them for the entire 4 year long duration of the LISA mission. Because they last in the LISA band, the millihertz band of LISA for pretty much the entire time. And what that means is that you're seeing a lot more of the orbits and the evolution cycle of that secondary object in the EMRI. Um, and what that means is you're able to constrain the parameters of these sources very well. Um, because you're seeing it so uh, well for so long, you are gonna have a template which matches all of these cycles perfectly for the entire duration. Or so you hope. You should have a model that can do that. And if you do have a model that can do that, then you can guarantee that you will measure these parameters to like really great precision. And then this opens a lot of different windows. First of all, if you want to do astrophysics, maybe it's even a little bit overkill. You maybe do not need this much precision. But the point is, you can set, for example, the massive black hole population, mass and spin constraints very well. And then you can do even more exciting stuff like tests of general relativity. So there are these the no here theorem, which basically tells you how the higher order multipoles of a black hole relate back to the mass and spin of that black hole. So you can basically use constraints on the mass and spin to see if what you observe is consistent with what general relativity predicts, for example. So you could do stuff like that. I think there are even more sophisticated models for testing basically beyond vacuum GR, beyond GR theories. Um, and all of that requires really high precision that extreme mass ratio inspirers uniquely offer you, which is what makes them interesting. There are other things. For example, you can also do astrophysics with them. So these systems are basically like a primary black hole, a supermassive black hole, and then a very small object orbiting around it. These systems are generally found in the centers of galaxies. And these galactic centers are really astrophysically rich environments, which means there might be an accretion based on just some third body interactions happening very close to the vicinity of the element. And because of that, basically, you can again make use of this long expiral duration to measure with good precision what are the properties of these accretion disks, whether or not they are third body present in the vicinity of the system, etc. So you can really start to gauge the galactic nucleus in galaxies using extreme mass ratio observations. Yeah, these are at least some ways in which I know the MVs can be really good probes of astrophysics and fundamental physics as well.
So everything is you are doing is related to Lisa, and Lisa is going to space, not like LIGO, which detects merger happening in the universe from Earth, but Lisa is going to space, and three spacecrafts are separated by millions of kilometers. So
Mhm.
what becomes visible only when you build a detector in space, but but that simply you cannot see from the ground. So what is the nature hiding from us?
Yes, I think again, Lisa is very different from LIGO in a way because LIGO, so all of these detectors have like a sensitivity bucket, which basically tells you what frequency range are the detectors the best sensitive. And for LIGO, that range is somewhere between 10 to 1,000 hertz. So this is like high frequency LIGO where detector emissions. In the case of LISA, the detection with this bucket lies somewhere in the millihertz band. So you will expect to see from like 10 to the minus 4 all the way to 0.1 hertz. Is the main sensitivity band of LISA. So it's like 2 or 3 orders of magnitude lesser than LIGO. And this is exactly why LISA will see a very different set of astrophysical sources than LIGO, including extreme mass ratio inspirals. So as I said, there are other sources like massive black hole binaries. So these are like really massive, millions of mass corresponding binaries, again found in galactic center, very galactic models. And because of their high mass, these sources emit gravitational waves which are less low frequency of the millimeters. Least are really sensitive to that. It will also be sensitive to the early spiral phase of galactic binaries. So, for example, these comparable mass objects, which will be merging in the light wave, these sources at the early spiral phase because the early spiral phase that at a larger separation emits gravitational waves which are at a lower frequency. And this low frequency early spiral phase of galactic binaries is what we also expect to see a lot of with the LISA detector. There are also some quote-unquote exotic sources, for example, sorts of cosmic strings theory with respect to the seen in the frequency band of LISA. There are also the hyperbolic encounters. So basically, two objects which are on an unbounded trajectory with respect to each other. So they come very close, interact once, and then this fly away. These are two very similar a string like um effect within the visa band like just a blip. And there are some people working on whether or not you can actually detect them with visa. And one more exciting source is intermediate mass ratio inspiral. So there are like these mass ratio thresholds that you set. So for example, for a massive black hole binary, it's mostly comparable mass. So the mass ratio would be something like 0.1 at max. And with this extreme mass ratio inspirals, your mass ratio would be orbiting with -5. But then there is this interesting population of sources called intermediate mass ratio inspirals, which lies somewhere in the middle. So you expect to see higher rate of them because they might not be just constrained to character center. Um, and yeah, anybody one kind of interesting science very well. Probably not fundamental physics, but surely something like astrophysics. They can do a lot of using intermediate mass ratio inspirals as well.
So you have contributed to fast EMRI waveforms and you authored your own stable EMRI Fisher. And that's your own, not a contribution to someone else's project. So, you built it from scratch. So before we get into technical what it does actually, I want to understand what frustration or a specific failure made you decide to build it. Usually when someone writes a new software, it's because the existing approach broke in a specific. So in your work, what was actually not working with the existing one, or we actually need new one for the like Lisa mission which you are working.
Yeah, so I think so. The stable educational project actually originated out of another project I was doing with the collaboration with people in France. And what they wanted to do was create a catalog of MUs. So basically, synthetically create a population of MUs and try to see using that population what kind of data analysis we can do. And because this was a bulk study of like a variety of different sources with different parameters across the entire parameter space, uh, doing like MCMC inference over the whole space is going to be very expensive. So, sort of like a middle ground then is that you do Fisher information calculations and use those Fisher information matrices, uh, which can give you like a linear estimate of what are the uncertainties in your parameter that you expect for each of these sources. Um, so, this is where the project originated. And we had to make this code essentially because none of the existing code to calculate these Fisher matrices was working well, right? So it was just unstable. There were so many different things you had to take care of. You had to manually insert different numbers, and there was a lot of trial and error, manual trial and error that you had to go through in order to get something that you can somewhat call stable. Okay. So that's sort of where I came in. I wanted to you know, create something which, okay, it still is not guaranteed to, completely solve the problem, but something which makes decisions which can be backed by, logic essentially. So how do you calculate? So what we do a lot of in this code is finite differencing. So numerical derivative calculation of the waveform itself with respect to the parameters. And this finite differencing, because our signal, our template is very oscillatory, calculating those derivatives is very difficult, stable. So a lot of what we do is try to streamline the process of calculating these derivatives, make sure that we go through a number of different answers and choose the best one in order to make sure that we are choosing the most stable version of this derivative calculation. We give the user a lot of freedom in choosing what order of derivatives they want, what is the finite difference delta they want, etc. So the main sort of, I would say, novelty of this code is to try and make the whole process automatic in a sense, so as to reduce your human input as much as possible, so that there is not as much fine tuning needed by, or not as much uh, basic tuning needed by someone, and most of the effort really goes into fine tuning whenever necessary, which is where the focus should be, in my opinion, anyway.
Yeah. There is something unusual about your situation that I want to sit with for a moment. Your entire PhD has been building tools for mission that has not launched yet. Lisa doesn't exist yet. So you are preparing for something that might arrive years from now on. How do you stay motivated when things you are building towards is that far away. What does feel like to write software that nobody can fully test it because the universe had not spoken into detectors.
Yeah, I mean, so um, there are two answers to this. First of all, uh, the more practical answer is ESA, although it hasn't launched yet. I think we pretty much know for sure that it will launch. So it has already been like adopted by the European Space Agency. The satellites are already under construction. There was a prototype that was reviewed, I think, early last year or something. We know for sure it will launch. We're like very tightly. It's almost like a consortium like what LIGO has right now. It's that deep of a network which is working alongside the instrumentation team, alongside the theory groups, etc. And to make sure that we can deliver the mission. So I'm sure it will like, happen eventually in 2030s. And then the other part of my answer is um, for me, it really doesn't matter whether or not it actually even launches. I mean, of course, I want it to launch. I want, all the stuff that I'm working on to be useful at some stage. But for me, more than that, at this moment, what motivates me is not really that, what I'm developing today might be useful 10 years later. It's like I made this interesting thing which can apply very neatly to this particular problem. Right. I made a stable StableEMRIFisher code which can solve the problem of finite differencing for or waveforms in general, right? And that's why like I try not to like work on projects which tie me to a particular, very niche part of the project. I try to do stuff which is quite generic. I try to do I try to solve problems which are like either more mathematical in nature, so which applies broadly to any sort of gravitational wave or any sort of problem in data analysis, or I develop codes which are widely applicable. So, for example, stable EMRIFisher, although it's called that way, you can directly apply it to other waveform models as well, as long as you have them available. So you can apply them to even LIGO based templates if you have those models available. Um, so that has already always been my goal to sort of not constrain myself to a box or um, not just pose my research in a way that is applicable only to one particular place. Um, and yeah, I think hopefully that continues.
People don't realize that these missions are not just particular from one field. You need instrumentation, you need electronics, you need physics, you need mathematicians, you need software engineers, you need builders, you need someone to launch your spacecraft into the space. You need lots of people to work on this one particular project. Then we can understand the whole universe. So what do you feel when people say that work on something which had direct impact on humanity right now?
Yeah, I think so. At some level, I think I can sort of um, empathize with people when they say that because I mean, of course, I'm not like ignorant about the fact that there are certainly many, more directly impactful fields, for example, medicine or, just hospital staff or whatever, places where I could be contributing today and I'd be more quote unquote useful to society directly, right? But then at the same time, I feel like academic institutions themselves play a huge role in trying to like inculcate that sort of critical thinking necessary for roles like this to even work. So I would say thinking that, if I'm working in like a space-based mission that will launch 10 years later and developing pipelines for it, I don't think it voids me of contributions to society today because I work with a lot of students. I work with a lot of postdocs, professors, etc. All of which, not just in myself, but also with the people I work with, inculcates a sense of, you know, critical thinking, We develop all sorts of new tools, not just codes which are useful, but also fundamental techniques in statistics, um, in some level in mathematics as well. Of course, I don't mean like we invent new maths by no means, but things that are of practical use to the community at large. And all of that sort of helps, in my understanding at least, helps develop the sort of environment we really need for even like people who want to go into medicine in the future. It provides a platform for them to really express themselves, make sure that they're able to contribute in one another. It's sort of a launch pad in a sense, even if people want to like do something more quote unquote worthwhile. Um, so I think it's very intertwined with society. Of course, if European Space Agency is going to launch the LISA mission, it's not going to happen in a vacuum, right? Like they're going to employ people to do that. Similarly, if we are going to write code which is going to be used in the mission itself, they're not going to send out codes that is written by Shubham Kejriwal, who is like a physicist. They're going to hire a software engineer to basically re-evaluate all of our code, make sure that it is written in the most efficient form, so that they can use their very expensive data centers to calculate it efficiently. And all of that is again going to employ more people. So it sort of is very closely tied with a country's GDP, how exactly all of these different entities function essentially.
So, when someone, some country is building a mission which is going to, detect something in the future, people don't realize that this is going to employ people. And if you're employing, you are giving job.
Yeah, no, I absolutely agree with you. This one workshop I was attending last year in ICTS, um, one of the things I heard was, you know, the kind of research that happens the most commonly in India is more theory oriented. And one of the reasons for that is because it needs the least infrastructure, is the most accessible. But I feel like if we don't create the avenue for people to even, think in a more sort of data analysis or like more computationally intensive sense where you do need infrastructure, then you're never gonna, start churning the engine which is necessary to make this almost like a self-sustained cycle where you employ more people to run your data centers so that, you can also do fundamental research at the back of it and the cycle continues. So I don't know. I do agree with you completely.
So, ICTS, you went for the gravitational wave school. Summer happens in
Yeah,
summer.
it was a summer, not a summer school. This was in like March end last year. I think this was on black hole. It was mostly on the image formation, the black hole image, how exactly you can calculate the light paths around the black hole, etc. So mostly to do with MHT simulations, which can enable you to do that. Or sort of offbeat from what I do generally, but I went anyway because why not?
Yeah. So when you see, you have worked in Singapore and also other places. So what is the main difference you have seen? Work you have come to ICTS, and ICTS is one of the best institute for theoretical physics in the world, not just India. In the
Right. Yeah.
world, it is best research coming out of it. But the cultural difference there is. So what you see here and which is not there, and what is there which is not here. What is the pros and cons like working here and there?
Honestly, I didn't see. So, okay, a general sort of thing I see in Indian institutes, which I don't see outside, is the sort of like hierarchy which is implied every time we call our seniors sir or professor or whatever. That is generally missing from any institute abroad, but to my surprise, that was also missing from ICTS. So, in that sense, I never thought, that uh, it didn't speak out to me as, limited by that sort of a implied hierarchy between a student and a professor or whatever. Um, Beyond that, I think I had really good food at ICTS, which I missed back in Singapore a lot. So
Exactly.
uh, throughout the 2 week summer school, our lunch was covered. Actually, no, the breakfast, lunch, and dinner was covered in the mess. So we didn't have to think about food at all. And this is something which is always missing from places outside. And I'm very grateful that they did that. And other than that, I think there really isn't anything that I can say which is like, um, no, I don't know. I don't think I can say anything which was like missing at ICTS really. Um,
ICTS is best in everything because the people who
yeah,
built it.
maybe I started with the wrong institute. Maybe then if I went to some other institute, I would have been able to give you many more differences.
One problem I see with ICTS is the distance from Bangalore. It is very far from Bangalore. I mean, you need to book a cab, and the last time I visited last year, it was like hectic.
Yeah, but I think that is like true for most institutes, research institutes
Yeah,
specifically. So where I'm going now for my postdoc, it's called the Max Planck Institute for Gravitational Physics. So it's in a township called Golm, which is a part of a city called Potsdam, which is at the far outskirts of Berlin. So it's like the outskirts of an outskirt of Berlin. So it's like a long travel time. And I think this is like a common thing I see across Max Planck Institutes in Germany as well. I think NUS is an exception. It's quite near the city center. But NTU, Nanyang Technological University, another very famous university in Singapore, it's again at the west end of the city. So I think it's a common trend. I don't know. Yeah.
yeah. There are lots of Max Planck Institute in Germany.
There is this Max Planck Foundation, which funds all of these institutes. And the main sort of concept behind Max Planck Institutes is to set up a center where you do very specific science, right? They are generally like built around these directors, which are sort of the field expert for the institute which is being set up. And then it's for them and their colleagues to set up essentially a hub for you know the best kind of research you can do in a particular field. And then the government, I think, tries to give you the best infrastructure necessary to enable it. That's as far as I can say about Max Planck Institutes. These are very sort of um, a diverse set of institutes. So within the same cluster where the Max Planck Institute for Gravitational Physics is, there's also one for colloidal physics and one more which I'm forgetting. So essentially, like st- uh, institutes which have very little to do with the kind of research we are doing within the same cluster. You talk to those people as well when you go out for lunch or something. Um, that is sort of the whole you know motivation behind these institutes, as far as I understand.
Yeah. Let's talk about your PhD. So, what mistakes during your PhD changed how you think about research? Not a small mistake, but a real one. When something broke or failed and you spent months going in the wrong direction. What did that teach you? All those success wouldn't have taught you.
Um, there have been many such instances that I'm trying to consolidate into one main takeaway. But for me, I think this is sort of like a personal problem. I start too broad. You know, if I am trying to solve something, I will try and approach it from like the most general case possible. And you can already imagine why that's a bad thing. So, and that's where like I get stuck for a very long time. What I end up doing is I develop a pipeline which I think is very generic, and then I try to apply it to generic answers. Sorry, generic examples, and then I very quickly realize that you know I have no way of testing whether or not this is working because it's so generic, and my intuition has stopped working at that level. So then you have to sort of strip that problem down, go back to the basics, maybe put the problem at a level where you can start to understand why exactly a thing is happening. And I end up sometimes wasting months going from that most generic version to a stripped down version, which I can understand. So, and I don't know if this is a common enough error. I think it should be, and which I try to like now try and advise against even for my own students. So yeah, that was a big one which has like basically loomed over me throughout my PhD in various projects essentially.
Yeah. So, I was asking, what are the biggest problems you would like to solve in next 10, 5 years? Or you want someone else to solve?
Hmm. So I mean from like the academic community at large, primarily working in cosmology and astrophysics, because I sort of started with, this problem of the Hubble tension. I think I would be very interested in seeing someone solve this problem of Hubble tension. I don't think, just the observations we have from just the CMB or just the standard candle observation are enough to solve the Hubble tension. Maybe you need some other perspective. And I think maybe gravitational waves can play a role there. There are already constraints from the observations of sources within the LIGO band on the Hubble constant. Of course, the measurement uncertainty is too large, so it's pretty much consistent with both the standard candle and the CMB observations. But I think as time evolves over the next decade or so, maybe these constraints will become much better. And I'm hopeful that it will play a role at least in trying to at least improve our understanding of the Hubble tension rather than it not like so that's what I'm hopeful from the community at large. Um, Me personally, I only think about things in the next like 5 year perspective, not broader than that, especially when it comes to research. Um, there are some exciting problems that I am currently working on. I find exciting. So within the LISA data analysis pipeline, there is this thing called the global fit. Um, and unlike, so what happens in the LIGO detector is that you observe one event at a time. Okay. And that lasts within your data stream for a second or a fraction of a second. So you have no problem of like multiple sources overlapping on top of each other. But that's no longer the case in LISA because Lisa will be observing for 4 years, and a signal like that from an extreme mass ratio in spiral can effectively last in the Lisa band for the entire duration. There can be multiple EMRI signals overlapping each other in both time and frequency domains. So then there is this pipeline a data analysis technique which is called the global fit, which is proposed to try and inform all of these sources simultaneously from within the data. So there are some different ways of doing it, but it's not ascertained how exactly you'll end up doing it. How do you search for so many sources within the data analysis, within the data stream? And then how do you infer the parameters of these different sources simultaneously? And I think it's an important problem to solve, of course, before LISA launches. And that's where my focus is for the next 5 to 7 years at least.
So I was thinking about the flip side of the work. You are building unknown. You're building something which is for unknown feature data set. So you think about what you are building and about making choices. Now you are not sure, right? Because you don't know what exactly the data set will look like.
So there are certainly like these blind spots. You make a particular choice, depending on what you think the data would represent.
Yeah.
And then maybe the data says something completely different, and then you're like stumped about um, what's going to happen. So there are again two aspects to this. First of all, as far as like, for example, Lisa's detector response is concerned, how do we know Lisa's response would be exactly how we model it and is not something completely funky? And that's because in 2015, there was this LISA Pathfinder mission, which tried to estimate what the LISA sensitivity would be. So this was like an Earth orbit satellite. And I think the sensitivity estimates we could derive from this mission in 2015 were in fact better than our theoretical predictions. So things were working fine. And then the other aspect then is that there are checks within the pipeline to make sure that we can exactly deal with situations like this. So, for example, there's this whole program of LISA data challenges. And what these are is basically like within these data sets. Okay, so these are like data sets in which you have massive black hole binaries, galactic binaries, extreme mass ratio inspirals, some version of the LISA response, etc. And then it's just released to the community to do blind global fit over or blind search over. So the community, the people in the community do not exactly know what is injected. Of course, you have that information if you want to, but the point of this blind search is exactly that, right? Because eventually you would want to add glitches within the noise, maybe gaps from downtime, etc., and see how exactly the current pipelines react to them, whether or not they are robust enough to deal with these unexpected, artifacts within your data itself. So I think this is an important thing to keep in mind. Even astrophysically, you could have like a beyond GR deviation or whatever, which acts in a way that you just don't have a template ready for. So how do you deal with that? These are certainly considerations that we have to take into account if you want to do robust data analysis. And you should also be aware how large is a potential bias you can get, or how much does it impact your final answer, depending on whether or not you're able to get rid of these problems. So yeah, there are multiple ways of dealing with it, and but anyway, it's very much under development how you deal with these problems as well.
Yeah, because like data is coming and you don't have a template for that. How you tackle the
Mm.
problem? It's very complicated.
Yeah, that's fair. Yeah. That's
So
why
what is
like there's
the
a lot of pressure even on like the waveform development groups to try and deliver these templates within time, because otherwise you just everything after that falls apart if you don't even have templates to work with.
so you develop these templates from numerical relativity.
So in the case of extreme mass ratio inspirals, there is a perturbative approach. So essentially you um, Taylor expand in a sense the Einstein field equations in terms of the mass ratio. So the mass ratio, the ratio of the two masses of the process, it's a very small quantity, 10 to the minus 5, roughly. And that's why if you expand about it, you find that the first or the second term within this expansion is already good enough to accurately model the template. So you take this sort of analytical approach. Of course, there are semi-analytic, let's call it, because then the actual data generated is calculated numerically. Um, but it is a semi-analytical approach in the sense that you don't really just throw general relativity or Einstein's field equation into a computer and hope for the best. In a sense. I mean, numerical relativity doesn't do that either, but it's sort of different from it anyway.
So what advice you would give to students who are currently in undergrad, and would you recommend them to come to gravitational physics?
Oh, yes, of course. We always need more people. But
Yeah.
I would say if you want to do gravitational waves, um, LIGO is good. But I think the more exciting science is where things are less developed. So again, pipelines like in LISA, there is also this third generation of ground-based detectors coming up, which have similar timelines as LISA. So the Einstein telescope or the cosmic explorer. If you're interested in gravitational waves in several aspects of it, even theory or data analysis, I think don't just restrict yourself to one mission or one particular aspect. Try and explore it all, especially if you're in undergrad and maybe like in second or third year. I think you can take up a lot of like short-term projects in order to really understand different aspects of the field and ascertain which part of it really speaks out to you if you really want to go down that direction. Or if none of that speaks to you, then you can still have fun to pick something else.
Yeah, LIGO-India is also coming up, so it will be a huge
Yeah,
opportunity
absolutely.
for
India is
Indians.
another great opportunity in the future.
We'll need everyone. Every from every field, we will need people, not just from physics. So it is
Yeah,
a huge opportunity. We
absolutely. And
talked about.
another aspect of like gravitational waves is that of PTA, pulsar timing arrays. These are like very low frequency gravitational waves, nanohertz. And the way you do that is you don't even have like a direct gravitational wave observation in the sense of like an interferometer. But what you observe are the pulses coming from, neutron stars or pulsars. And for that, you basically need radio telescope. And India has some of the best radio telescopes in the world,
GMRT,
which
we
work
have GMRT
in,
in Pune.
yeah, yeah. So that works in collaboration with other radio telescope facilities across the world and is a part of like I think the European Pulsar Timing Array Consortium as well. So if you are interested, I think that is another very exciting field coming up, which is currently already accumulating data and will continue to do so for the upcoming unforeseeable time as well.
So you read some apart from academia, pop science or maybe something books which you have read. Would you like to recommend?
It has been so long. I think the last one I tried reading was Brian Greene's Theory of Everything back in like 12th grade or something. I've even forgotten 90% of the content from it. I generally like prefer nonfiction. So the less interesting stuff, I try and understand, like, for example, the stock markets, bond markets, stuff like that. I bought this book called Bad Money, which talked about like the financial crisis and I think the early 2000, stock market, some sort of scams within the stock market system. So I always find these sort of non-fiction, real thrillers more interesting. Um, but no, no such like very exciting books that I could probably talk about at the moment, unfortunately.
Yeah. So you mentioned stock market and there are hedge funds like Renaissance or Jane Street, which are hiring physicists and mathematicians to work with
Yep.
them. So do you think this is a brain drain for physics community or mathematics community?
Um, I think there has always been like an attrition of true physicists or mathematicians towards industry, and I think it's quite natural. If you tell me, I can use the same amount of brain power and earn like 3, 4x more money. I mean, it sort of makes sense. Um, and I also find it really fascinating, you know, why exactly would like people around me who are doing physics right now, especially in data analysis, why are they doing physics when they can get the same amount of money and be in industry? So I
Y-
ask this question to every single person around me who's like a professor level or above. And the common answer I get is it's all about freedom. So someone at a professor level or above, these people are basically making decisions for themselves. Of course, they have to play the game where they have to apply for grants, they have to cater to the department requirements in their university, etc. But except for that, at the level of what kind of research they want to do, what kind of students they want to hire in the next round of PhD, etc. It's completely on them, right? What kind of postdocs they hire into the group, etc. So I think it comes down to that sort of freedom in doing what you want to do. Whereas, of course, in a scenario, in an industry scenario, it's sort of money driven, right? There is one very clear aspect that you're trying to optimize over without caring so much about all the other things. And the common answer I get is it's essentially for that. You can either choose money or your freedom, and these are the people who chose their freedom. And don't get me wrong, I think I also heard this from someone that this is actually like a minority of the entire, community. So the number of PhDs that we produce, only a very few fraction of them actually convert into people who go into academic careers. Most of them transition into industry, and rightfully so at some level. Yeah.
there is a very few posts for them, so there is just natural path they have to go to industry because they also need to work for their they need money to survive.
I don't hold them. I don't blame anyone for like choosing industry over academia or something. I think everyone has their priorities. And sometimes it's not even about, what kind of work you're doing. As long as you enjoy, for example, coding, maybe you don't see a difference between, a quantitative whatever software engineer versus like someone who's working to write stable EMRIFisher, right? But if you care more deeply than that about the failure working in, maybe that's where the difference starts to creep in. And maybe for the large population, that doesn't really matter as much.
Yeah. Thank you, Subham, for joining. Keep
Shailesh,
doing some
thanks
great
for
work.
having
And
me. You're
yeah,
doing a great job. I think this is great to have exposure and keep on keep.
yeah. Thanks.
Thank you.